I'm Yannis Alimonos from the Computer Vision Lab in the Department of Computer Science at the University of Maryland, and I will be chairing this session today of the future leaders in robotics and AI. We have two speakers scheduled, Chahat Singh and Faith Johnson. Each speaker will take 20 minutes to make his or her presentation, and then there will be about 10 minutes for questions. Okay, so I would appreciate if the speakers stick to this requirement so that we can negotiate with time properly. Okay, so the first speaker is Chahat Singh, who is a postdoctoral fellow at the University of Maryland Robotics Center. Chahat studied in India, and he came and he got a master's degree in robotics from the University of Maryland. And then he joined the PhD program in computer science, and he did his defense last year. I was his advisor during this journey, and he has published extensively in this field, and he is also somewhat of a public figure. He has given several interviews, especially one with the BBC that is quite well known. So Chahat will speak today about minimal perception, enabling autonomy in palm-sized robots. Chahat, the stage is yours.
Thank you. Thank you so much, Professor Yannis, for the introduction. Share my screen. Can anybody see my screen? Can anybody hear me? Anybody? Professor Yannis, can you hear me?
Yes, yes, yes,
Okay.
we can hear you.
Okay, so I'm going to talk about minimal perception, a framework to enable robot autonomy in resource-constrained robots. So the first question I will ask is, fundamentally, what is perceptions? So philosophers have been debating about this word over decades, but the most common and suitable definition for this talk is that perception is the organization, identification, and interpretation of sensory information in order to represent and understand the environment. Or in simple terms, what do we see, hear, touch, and feel, and how we represent the world around us. So why is perception a problem with small robots or robots that have so much constraints? So these perception issue comes with the limitations of memory, limitations due to sensors, as well as power constraints. And this is exacerbated because of the limitations on size, weight, area constraints, right? So if you talk about resource-constrained autonomy, so let's move from the existing autonomous robots to the future of resource-constrained robots, right? So this is what on physical millimeter scale, a standard research-grade drone looks like. And going from there to over the years from 2016 to 2019 and 2020, and these works going towards 2021, is the question we want to ask is, how can we have safe, scalable, and robust autonomy on these palm-sized robots? And the answer to this question is with nature, because nature has spent 3.8 billion years on research and development through evolution. And if we see hummingbird, which is one of the smallest flying beings on this planet, which has 120 millimeter of wingspan, weigh 250 grams, and has about 1 billion neurons. And you would see that they solve a lot of tasks with ease. And so does a being that has 1,000 times lighter in terms of brain weight, and that is a honeybee. And they're trying to solve similar day-to-day tasks, but in a very different way. And today we learn how can we learn from these beings. So the question is, what can we learn from nature? So I'm going to present the minimal perception framework which I worked towards during my thesis. So we can subclassify the entire framework into 3 basic modules. The first one is minimal information. What information is minimum that you require to solve the task at hand? Second is minimal sensing modality. What kind of sensor would you choose to solve a given task at hand? And third is data acquisition, which talks about what kind of data modification or what kind of sensor modification can you do before you acquire the data itself. So I'm going to talk about each module for now. So let's focus on minimal information model. So like I said, what is the minimum information that is required to solve a given task at hand? So let's take an example. And I want to talk about fundamental problems that occur in single images. Okay, so if I give you this image and ask you, can you find a gap or a hole in this clumsy pieces of paper? It's hard to find in these situations without knowing how far things are. And to find that in single image, it is very hard. But if I show you a sequence of images or a video, you can easily find these holes, right? So the idea is, do not rely on single images unless you know anything about the scene. So coming back to the question that how are birds and bees different? So let's look at an example how birds and bees are trying to find gaps like we saw in the last image. So take an example of a sparrowhawk. They have amazing vision, very complex navigation and brain functionality, and they're able to do these tasks very seamlessly. Versus if you look at a honeybee, life is not that simple because you don't have good quality eyes or computation power or vision. So you have to move around and find the gap, right? So one fundamental thing that we can understand from bee is also they don't understand how far things are in metric scale. They do understand the size of these gaps with respect to the body length. So one of the experiments that occurred in 2019, 2020 was if you show multiple gaps of different sizes in front of honeybee, the amount of pairing these bees have to do is based on how big the gaps are. So that shows that these don't understand how far these gaps are or what if in meter scale is it 1 meter away, 2 meter away, but they understand how big or small the gap is with respect to their own body. So the question is, what are the bees observing here? So just look at this, the hole that we just saw. So if the left side shows the 3D view and the right side shows what the bees see. And if the bee moves from left to right, you see the hole has moved in its vision from middle of the screen to the left of the screen. So if you join these vector spaces, right, you can map this also in a color map. And this is what is known as optical flow, right? So note that the farther points, the closer points that are on the wall have higher optical flow because the motion of the closer points are going to be bigger as compared to points which are lighter. And the motion of the points which are farther away is going to be way smaller, right? So this is fundamentally what optical flow is. And this is what we mimicked on our drones. So we are equipped with a single sensor, a single RGB monocular camera, rather than a LiDAR or a 3D camera. And we observe the scene from multiple views. And we compute optical flow between these frames. And we combine all these information to find where the gap is. And finally use that information, track and go through these gaps, right? And we show successfully and evaluated and demonstrated the proposed approach in many real world experiments with different settings and window shapes. And we achieved the speed up to 2.5 meters per second and accuracy of 85%. So, but the question is, do we need to compute optical flow? Because the previous experiment that you saw worked about like computation of optical flow was about like 3 to 4 hertz. The question is, why do we need to compute such an expensive optical flow for these fundamental tasks? So other things that people have done in computer vision is depth estimation. The question is, can we use monocular depth estimation method? That means that you have an artificial intelligence framework or a neural network that takes one RGB or a camera image as an input and tries to predict the depth map from this one single image. So right image that you see is a depth map, and the navy blue or the dark blue color is representing the pixels which are very far away versus the yellow which is representing pixels which is very nearby. And the question is, if you focus on my entire body, you would realize that my legs in this representation are way behind as compared to my torso, which is not correct, as you know that I would be standing on one plane, right? So these depth estimations do have error. The question is, do I have to be relying on what I'm wearing or how I'm looking at that particular day? Probably not. So there are uncertainties in these estimations. The question is, what is uncertainty? The uncertainty is basically, as to quote the famous Socrates, that the only true wisdom is knowing that you know nothing, right? And uncertainty in computer vision and robotics application has been widely studied in the last 5 to 6 years. And there have been many applications from depth estimation, optical flow, odometry estimation, and disparity, surface normals, and etc. And what they have been doing is they have been using this input image. They have a network that tries to compute surface normals, and they have a network that tries to compute uncertainty. Now they combine uncertainty and surface normal in this case to have a final surface normal, which is, as you can see, is way more clean and more robust at the edges. But the fundamental question that I'm going to ask is only computing uncertainty enough? We believe so, and this is the result. So generalized deep uncertainty formulation for minimal perception on parsimonious robots. This was an article that was published and was on the cover of Science Robotics last year. And the idea of this formulation is we have a minimization function, which in this case is represented as HF plus lambda G, where F can be any quantity, any prediction. We will be focusing on optical flow, but it can be replaced with depth estimation, surface normal, and semantic segmentation, right? And G is a monotone function, and H is another function, which has the inverse nature of the monotonicity, right? So putting this equation, and the whole idea is if you insert the values of H, F, and G, and lambda, all these 4 variables, to certain values, you will have all the previous papers that have existed that deals with uncertainty. So it's a generalized formulation to compute any uncertainty. Now, going towards the application, why can and how can the uncertainty be used? Not computing the entire optical flow or surface normals or anything else, just computing the uncertainty in optical flow can be used for dodging, navigation, flying through these gaps, and segmenting objects in the wild. And let's see how that works. Right, so these are examples where the drone is flying through spaces and it's seeing objects, and because of the motion, it's we are able to estimate uncertainties in these images. And apart from just navigating, it can also dodge dynamic objects like like dodging a drone, and fly through unknown gaps like we saw, just by relying on uncertainty in flow. Right. So, but if you focus on a scenario where it's flying through forest, the idea between the depth estimation and the uncertainty is if you focus on these maps, like the first one is an input image, second one is the ground truth depth. the same color combination applies here as well. Yellow means nearby, dark blue means farther away. And this is then state-of-the-art monocular depth estimation method. And this is our approach. Notice that in the red part, you will see that the pixels of the branches are not even being detected by the depth estimation model, which relies on one single image, versus our method, which can get that value. Right? Moving to the second part, choice of sensor. Right? What kind of sensors do we want to adapt? Right? If you look in nature, that perception systems have been parsimoniously evolved from frogs, jumping spiders, and bats. And these bats are masters of flight. And even at night, they prove that perception goes beyond their eyes. And the way they do that is they're not blind. Like everybody thinks that they're blind, but bats are not blind. They combine information from their multimodal sensor, which is echolocation, and their eyes to precisely perceive their surroundings. So this is a paper that I'm going to present, which is tiny there. So if you observe the scene from multiple views using two sensors, one is RGB camera like you saw in the back, and the other one is super sparse 8x8 depth sensor, which is deployed on variety of robots, which observe the scene from multiple views. So the camera sees these RGB images, and the sparse depth map, you can see it's super sparse. And what we are trying to predict is dense depth map. And we are replacing the industrial standard Intel RealSense and Connect robots, Connect sensors that are way bigger in terms of size, power, and even price.
Chahat, you have
Yes.
5 more minutes.
Yes, thank you. So the idea is you can deploy these on smaller robots, which takes inputs of RGB images and sparse depth maps, and infer depth prediction that you can see on the bottom right to solve these varieties of tasks. And because of these robots these sensor suites are very small, you can put at all the edges, all 4 edges, right? So you get omnidirectional vision, which enables you to navigate and dodge obstacles which are in all the directions. So I'm going to move to the third element, which is minimal data acquisition. Question I'm going to ask is, can we modify the sensors? Can we modify the way we perceive and do some sort of segmentation or processing before the data is actually arriving on the sensor itself? So modifying camera aperture is very common in photography. One of the word you might have heard is a bokeh effect, which is observing or taking an image with a pinhole camera or a camera that has a very small aperture or opening. You get a sharp image, versus if you open the aperture wide enough, you get the blurred image. And the farther you go, the blurred the background, the more the blurred the background would be, right? So the idea is, can you modify sensors like these? On an example, you can see that photographers have been using these custom art and pasting. And if you see point sources of light, you get these shapes, right? So I'm going to present based on this concept, coded visual odometry or coded VO. So what we did is we took out the camera, we added a thin piece of glass, which is basically in micrometer scale, to get this bokeh effect. Now, because this is coded because we are coding these depth maps. So it ranges from 0 to 2 meters, and it's at different width at different points in space. So by doing that, what happens is it gives you a blurred image. So the left image is from a standard camera, and the right image is what you would see using these coded cameras, right? So you get blur. Now this blur, like we discussed with bokeh, is a function of depth. Now we utilize this information of the blurriness, and because that is a function of depth, we can recover metric depth information using our network. So on the third image that you see is a depth estimation from our neural network, and the right is the ground truth, right? And unlike all these other state-of-the-art methods, monocular methods that uses one single RGB images, right? Our method can also give meter scale as opposed to other methods, right? So the benefit of getting the metric scale here is if we combine these information from a coded RGB camera or a standard RGB image with the predicted metric depth and use that in conjunction to predict odometry, we get odometry with scale. That means we know exactly in space how much the robot has moved in meters. So that's the entire idea of having or modifying the coded or modifying the camera aperture with these coded devices. That's it. So to conclude the slide, so this is an overall framework that we have to rethink from the cognition level to the sensor level, right? What kind of information that we require to solve the task at hand? What kind of sensors would you require minimum to enable these autonomy on these small scale robots? And the last one would be, can you actually go inside the sensor and modify these sensors so you can actually get more information that was not present before? And second is, you want to develop these minimalist, parsimonious, not generic, but a very specific framework for these tiny robots to enable autonomy. So you can have efficient task completion. And you need to think robots as embodied agent to tackle robotics problem and think from a hardware and software core design perspective. So I would like to thank all the sponsors that have helped and enabled this research and all the collaborators and co-authors over the years. Thank you.
Thank you, Chahat,
Mhm.
and thank you for keeping to the time.
Sure.
Very good. Okay. Now there are some questions from the audience. All right. So the first question from an anonymous attendee.
Mhm.
Is tiny depth similar to depth completion?
So the answer to this question is that tiny depth is very similar to depth completion, but the difference between this and depth completion is in depth completion models that you see from sparse LiDARs, you get accurate or relatively accurate point in space where you are getting depth estimation. What this sensor, this particular sensor gives you is a range of space where you get the depth. For example, it gives you that there is a particular point in space that is 5 meters away within a cone of 5 degrees. It doesn't tell you where it is. So imagine you are looking at the edge of a shelf, right? So there are pixels which are 3 meters away and there are pixels which are 5 meters away. So the information in that 5 degree of cone that you're going to get is going to be the median of all the pixels in that. So it's very similar, but in depth completion, you will get one particular value, which would either belong to in front of the shelf or behind the shelf. In this case, it represents the median of the entire cone.
Okay.
Yeah.
Next
Yeah.
question from a graduate of our lab, Kaniska. Very nice to see you, Kaniska. I don't think I can hear you, but Kaniska is asking you, is the tiny depth sensor off the shelf or custom designed?
So we rely on the hardware that is developed by companies. So for example, we use standard Raspberry Pi cameras for an RGB camera, and we use VL53 by ST Microelectronics, which can give these sparse depth maps at 15 hertz. So we combine these and we have our own calibration procedure to actually find the relative transformation between these two sensors. You can buy these two individual sensors off the shelf, but the combination and the calibration has to be is required for all the depth prediction.
Okay. Then the next question, does one need to retrain tiny depth for using it on a different RGB plus T of F camera system? Or can it automatically generalize to new camera systems?
So that's a very good question. So the first thing you would require is to understand that for this particular network, it takes input as 8x8, or in this case, like 64 pixels of depth data, and it's been stretched to match the input RGB image, right? So the one thing you would require is to have the calibration done of your new RGB and TOF camera system. And you need to represent this time of flight output to an 8x8. So once you have that, it would generalize to any camera system in the world.
Okay. Next question. How near it is in future to have coded apertures on robots?
So it's a very good question. So coded apertures in computational imaging field has been known for over a decade now. So the idea to bring towards robot is that we need to think of having these coded apertures on very small cameras, right? So for the future, I would see the answer lies in the meta lenses. That is an emerging field which allows the fabrication of these tiny coded devices on a sensor which are like 1/3 of an inch, which is very common with robotics. And with this emerging field with meta lenses, I would argue that it's about 5 to 10 years in the future.
Okay. Next question from Troy Williams. Could you comment more on using small chip sensors on small platforms with limited batteries? If we use networks to infer the depth maps, this would limit the battery life of the small platform. How would you mitigate this issue?
Sure. That's a very good question. So this is another ongoing field that people have been working on, that how do you have neural networks that are optimized, that are quantized to a certain level, that have limited battery consumption. That is one. Second thing is even our tiny depth, if we talk about, we are running on a Raspberry Pi 4, which is with a custom motherboard, but it's a very smaller in terms of like if you talk about device or battery consumption, it is way smaller as compared to any GPU or off the shelf, even NVIDIA's Jetson devices, right? So that is one that we need to work more towards having quantization and in terms of neural network inferring, that how can we have better integrated model. And the second is hardware optimization that companies like NVIDIA and Intel have been working on over the years. So I think the integration of choosing the sensor and hardware and network architecture combined in one software hardware core design is the key to this answer.
Okay. The next question has to do with a video that you showed. In the video of the bird moving with high speed through the fence hole, how can it determine if it would fit through the hole from far away with high speed as it's moving with high speed motion towards the hole? What computation is required for that?
So the answer to this question is the bird, if the hole or gap is new, the bird might not know before it is very close to the hole. One of the things that birds do is they utilize their stereo vision as well. So when you are very close to the gap, your stereo sensors become basically a depth sensing system where you can infer metric depth in a very limited range, right? So from far away, it may not understand that or determine that it will be able to go through the hole, right? But if you are close enough, your stereo sensors can infer these metric depth. So it can understand how big the hole is with respect to their own body. If
Okay.
you have this, you would require one beam LiDAR at least to understand, or knowing the size of the gap.
Okay. And now the last question. Is tiny depth open source?
So this work is currently not open source, but after the acceptance, it will be open source soon.
Okay. Again, thank you, Chahat, for the inspiring talk.